Let's take a look at section 15.2, just going to cover iterated integrals. So our learning objectives this time, we'll define what the iterated integral is, calculate a couple of them, and then relate the double integral and the iterated integral using Fubinis Theorem. Last time we looked at what a double integral was, and we said that a double integral is just something that's defined as two integrals over a region R on our function of two variables related to dA, which is just an infinitesimal change in the area of whatever region we're integrating over. So a double integral is integrating over an area, whereas an iterated integral will do something pretty similar, but it will involve two single integrals over some region R that we just do together. So for an iterated integral, we'll still define our region R, except this time we're going to talk about specifically what it is. And for this section, at least, we're only going to look at rectangular regions. So we're going to define our region R to be the rectangle covering A to B in the X direction and C to D in the Y direction. And if our function f is integratable on the region R, then we define the iterated integral, or the iterated integrals, going from A to B and from C to D to be first doing whatever integral is marked on the inside, which in this case is dy, and then doing the integral that's marked on the outside, which in this case is dx. So what that means is that first we do just a standard single integral of our function f over, in this case, dy, but again, it would just matter whichever element we have on the inside. And then after that, doing an integral on our result to get a second integral, but this time in terms of x. So a couple of things to point out. First, this integral here that covers only dy, where it's going to be treating x as if it were a constant, that is a definite integral, which means we'll be plugging in values for y. So by the time we're done, this piece should be a function of only x, since we'll be integrating y out. Since again, it's a definite integral, so there should no longer be a y variable after we finish that integration, which means the resulting piece just comes out to the integral from a to b of a function that now depends only on x, and we're integrating in terms of x, which means our result is some constant number, or a scalar, being the word that we use in multivariable calculus. So by the time we take two iterated definite integrals over some region, our ultimate result should be just a number, as we'll see if we do the next example. So evaluating the iterated integral from 0 to 3 in the x direction and 1 to 2 in the y direction of the function x squared y. So we'll start by just doing the integration in the middle, where we're going to want to integrate x squared y with respect to y. So that should go to x squared times y squared over 2. And we're going to evaluate from 1 to 2 for the y's, and then multiply that by dx. So we have this inside piece where we're just going to look at, again, plugging in 1 and 2 for y, since that integral depended only on y, So we're just looking at dy. We're going to leave the x piece alone. Doing so means that we should get, well, we'll get 4 if we plug in 2 for y. We'll get 1 if we plug in 1 for y. So 4 over 2 minus 1 over 2 is 3 over 2. So let's just pull that out here and call it 3 over 2 x squared dx. And then we need to take an integral here, which should come out to, looks like x cubed over 2. Since we'll have x cubed over 3 times 3 halves, which ultimately should result in x cubed over 2. We integrate this thing from 0 to 3, which means we should get 27 over 2 minus 0. So as we stated a moment ago, when we take when we do iterated integrals on a definite region, our final result should be some scalar, just a constant number. So let's take a look at Fubinis theorem, which is going to tie together the two somewhat similar looking ideas of a double integral and a set of iterated integrals. So starting on the left, we have a double integral. Where we're integrating a function of both x and y over some region R and multiplying that by dA, which again is an infinitesimal change in the area. So that is a double integral, and it's represented with 2 integral signs compared to these other iterated integrals, which we have there and there, iterated. And in these iterated integrals, we're defining a specific order to take 2 separate single dimensional integrals. So we're either going to take an integral first with respect to y and then with respect to x, or first with respect to x and then with respect to y. And what Fubinis theorem says is that if our function is continuous on the rectangular region R, then the double integral is equal to either order of the 2 iterated integrals that we could do, whether that be first with respect to y and then x, or first with respect to x and then y. Let's change that color to be purple. So I'm going to use pink for something else. So one thing to notice, it seems like we were using green for y earlier, so let's keep that going. With our 2 different orders that we could take these integrations in, it's important that we match the bounds up correctly. So if we're doing y first, then dy is the interior of the 2 dy and dx pieces. And the bounds for y also go on the interior integral. While if the x is on the outside, then the bounds for x also end up on the outside integral. And if we want to switch the order, it's just important that those bounds follow the integrating factor. Like they do here. So visually, what these iterated integrals ought to look like are the 2 figures listed below. Figure 1 corresponds to the first direction that we could take our iterated integrals in, while figure 2 corresponds to the second direction. So that if we first take an integral with respect to y, we then get an area that we're going to pass through some function to ultimately get ourselves a volume. And we're passing that area through in the x direction, which is what we see in figure 1. Or if we do the x integral first, then we're going to pass an area along the y direction, as we can see in figure 2. But so that what that second integral should do is it's basically taking an area instead of just a single line and passing it through some shape in 3 space in order to ultimately end up with a volume, which is what we should get when we take a double integral. So our result here is a volume. And a volume, again, should be just a scalar or, a constant number. All right, so next, we want to evaluate the double integral that has the square root of y over x squared dA, where r is the rectangle bounded by 1 and 3 in the x direction and 0 and 1 in the y direction. So using Fubinis Theorem, if we set up this double integral, which should be the square root of y over x squared dA. The theorem we just looked at said that we can split this up into a set of iterated integrals, where x will go from 1 to 3, y will go from 0 to 1, and we'll keep that same function, square root of y over x squared. We'll want to do dy and then dx. Or again, we just want to make sure that those bounds and the integrating factors match up. So if we do that first integration, this one is going to be with respect to y. We will have an integral from 0 to 3. That part's for x, so we'll just leave that alone for a moment. And integrate our y piece. This will be 1 over x squared times y to the 3 halves divided by 3 halves. So that should be 2/3 y to the 3 halves. And we want to evaluate from 0 to 1. Close off that piece and then keep dx hanging out. So evaluate that integral and we should get another number. Somehow change that to a 0. That should have been a 1. This is 1 to 3 in the x direction. What do we have left over? If we plug in 1 for y, we'll get just 1, 0 for y, and we get 0. So I think that the y component integrates out to 2/3 times 1 over x squared, and still with that dx. And now we should be able to integrate this last piece. We have 1 over x squared, which should integrate to negative 1 over x. So negative 2/3 times 1 over x. And we want to evaluate this piece from 1 to 3. And see what we get when we plug all that in. If we plug in 3, we're going to get negative 2/9. And if we plug in 1, we're going to get negative 2/3, which would be 6/9. So ultimately that's 6/9 minus 2/9, which is 4/9. 4 over 9 should be that double integral evaluated. Okay, so let's talk about breaking apart some of these double integrals if we can. So if f is what we'll call a separable function, which means that if I have a function f that depends on x and y, but I can instead write it as the multiplication of 2 separate functions, one that depends only on x and the other that depends only on y, and I'm going over again some rectangular region, then I can separate out an iterated integral into a multiplication of two single integrals, just like we did back in Calc 1. So instead of having to actually take an iterated integral, I could take two separate standard integrals and then multiply them together. And again, the important part here is that we have a separable function f, and it must be separable over multiplication and not over addition. So if we have f of x and y equal to xy as an example, that's good. But if we had our function that was f of xy equals to x plus y, that's bad. We wouldn't consider that to be separable, because in order to be separable, again, it has to be separable over multiplication rather than with addition. Cool. So a quick proof, or a sketch of the proof of how this thing might work out. If we start out with just our double integral, which is over the region R, we can say that, what do we have here? Oh, let's actually change that dA to be, looks like we're going to do dy and then dx. dy dx, and let's keep the colors consistent. Slide that over just a little bit, make room for a dx to slide in. So this step right here is what we did with Fubinis Theorem. As we said that we could separate out a double integral into a set of iterated integrals that cover whatever pieces we wanted for for y and x, c to d for y, a to b for x. So that first step, again, we got from Fubinis Theorem. And then if we go into the next step, we're treating that first integral just as an integral over y, which means that in that particular element, g of x is going to be treated as a constant within the y integrals, just within the green space. So what I've done is I factored g of x outside of that integral, because again, since we're just integrating over y, it's going to treat x like a constant, and so I can pull any constants to the outside of the integral. So now what we have is just some integral that depends only on y, has only y in it. So when we do that integration, we should get just a constant number out, just some scalar. So now if I look at just the x piece, again, looking over here where that blue g of x is, it's being multiplied by a constant number, because the integral from c to d of h of y dy is just a constant number. So much like I just factored g of x out because it was constant, now I can factor that whole integral in terms of just y all the way out of the integral that depends on x to have a completely separated two integrals that we're multiplying together. And that's how we end up with this theorem, or at least a rough sketch of the proof that gets us there. All right. And let's use what we just learned to apply to a theorem we learned in the last section, which is finding an average value. So recall we said that the average value over a function was going to be 1 over the area of that region times the double integral of the function. This is going to be f of x, y, dA. So that was from section 15.1. So what we actually want to do here is find the average of the function provided, which is x times secant squared over the region that's defined as the rectangle with x going from 0 to 2 and y from 0 to pi over 4. So break all this down. And the area of our rectangle, well, in the x direction, we have a width of 2. And in the y direction, we have a length of pi over 4. So our area should just be 2 times pi over 4. Then, to actually do that double integral, we have a separable function because our function is x times secant squared of y. So I can separate those two pieces out. Also, if you went back and look at all of the other examples we did, those were all also examples of separable functions. So we could have applied this theorem at the end to any of the previous examples we looked at. But let's go ahead and apply that theorem here. I have a separable function, so I'm going to separate it out into an x piece and a y piece. So let's start with x, where we're going from 0 to 2 of just x dx, and multiply that thing by the integral if we just do the y component. Just the y piece is separated out. So we're going from 0 to pi over 4 of secant squared of y dy. All right, and simplify this thing where we can. 1 over, well, so 2 times pi over 4 is going to be pi over 2, and then 1 over that is going to be 2 over pi. So let's put that in. We're integrating x from 0 to 2. So that'll be x squared over 2 from 0 to 2. So 4 over 2 minus 0. That part will simplify to just 2. And then let's actually show some steps over on this other one, since secant squared isn't a function we run into all that often. But if you remember back from Calc 2, we found that secant squared is the derivative of tangent. So if I integrate secant squared, this is going to get tangent of y. And we'll integrate that thing from 0 to pi over 4. Might as well keep that thing in green. All right, and let's evaluate this thing. So we still have 2 over pi times 2 times whatever we get when we evaluate tangent of y at pi over 4 and at 0. Well, at pi over 4, it's going to be 1, and at 0, tangent is going to be 0. So we get 1 minus 0. So ultimately, this thing shakes out to 4 over pi. And then since we showed the full evaluation of the y component, let's go ahead and also show the full evaluation of the x component, just for funsies. So what did we say we had? X squared over 2, and we're going to evaluate that thing from 0 to 2. Bring it back inside the lines. All right, cool.